NMR system, although it's not labeled very well, but you've seen the basic components here. Did I tell you my DuPont story? I think I did. Not.
Oh, the elevator.
Yes.
Yes. Yeah.
When I was living back east, I lived in Delaware, and that's where DuPont's headquarters is. And Bain Research Facility built a building that was just an NMR system, and it didn't work. They spent millions and millions and millions of dollars, gigantic magnet, much higher than anything you can get commercially, and they fired it up and it didn't work. Well, it sort of worked. It worked intermittently, and it just drove me crazy. Turned out that they had an elevator in the building at the other end of the building, and the movement of the metal in that elevator disturbed the magnetic field enough so that they weren't able to do, I mean, it just went on the fritz when anybody was going up and down the elevator. Finally, they shut down the elevator, made everybody walk up and down the stairs, and it worked. But, real expensive system, but again, why would you go that, why would you build something that big? For the very reason we discussed, the more resolution. The stronger the magnetic field, the better I can see my runway. Does that make sense? Okay. Here's what we see from an NMR, in an NMR spectrum. Here's the upfield, and here's the downfield. And the more we go down this way, the more de-shielded we are. Does that make sense? And so in this compound we were looking at before, methanol, these hydrogens appear here. This hydrogen appears here, downfield, because of the presence of the oxygen. Lower field. Now, in order to standardize the system, we use an internal standard called tetramethylsilane, abbreviated TMS. Because silicon is lower on the periodic table than carbon, the electronegativity of this molecule is such that it enriches the electron environment around those hydrogens in the tetramethylsilane. So tetramethylsilane signals pretty much farther upfield than anything else we encounter, and so it serves as the 0 point. Everything else is downfield from tetramethylsilane. Understand what I'm talking about? The covalent bond between silicon and carbon is such that the electrons are drawn toward carbon. Carbon is more electronegative than silicon. That tends to enrich the electron environment around the hydrogens on the carbon. Are you okay with that? And so we spike our samples with a little tetramethylsilane, and we see a little spike for it, and that's the 0 on our scale. We use it to set 0. Everything else is measured against it. In the previous slide, this is tetramethylsilane. Put enough in there, just enough in there so we see a little spike. Chemical shift is measured in parts per million, either parts per million in terms of change in magnetic field strength or change in radio frequency. It can be done both ways. The chemical shift is the same no matter what the magnetic field is. The chemical shift has to do with the electron environment, not the magnetic field. And so if there's a chemical shift of 1 part per million, it'll be 1 part per million on a 300 megahertz system or a 60 megahertz system. Okay, it doesn't really matter. So here's an example. Tetramethylsilane signals at 0, and what I've got up here on the top is a 60, this is a 60 megahertz system that's been cut off here. And I see the what is mega, what is the prefix mega? Million. So this is a 60 million cycles per second. That's the frequency of the electromagnetic radiation. And so right here, this is 60 hertz less. 120 hertz, 180, and so forth. So each division is 1 part per million in terms of the frequency flow and downfield value. Does that make sense? If I have a 300 megahertz system, okay, here's my hertz. Now 1 part per million is not 60 hertz anymore, it's going to be 300. 2 parts per million would be 600 and so forth. Because of that broadening of the part per million range, I can see the peaks better. I can see resolution in a bigger system that I can't see in a smaller system. So far, so good? Okay. And here's a problem. I don't know that it's worth our while to go through it, but we've got a 300 megahertz spectrometer that records a proton at a frequency of 2130 hertz downfield from tetramethylsilane. Determine its chemical shift and express the shift as a magnetic field difference as well. Okay, predict the proton's chemical shift in a 60 megahertz system. So what we did is we take the downfield shift, which is 2130 hertz, over the frequency used by the spectrometer, which is 300 megahertz, and that turns out that that's a downfield shift of about 7.1 parts per million. Does that make sense? By the way, what signals at about 7 parts per million? Do you remember? Alcohol's almost, they're about halfway down. They're aromatic hydrogens. Hydrogens on a benzene ring. Remember that? And so this would be typical for that. The chemical shift, okay, in this, then 7.1 in magnetic field strength, and a 300 megahertz system uses a magnetic field strength of 70,459. So I figure out what that value is in Gauss. So I take 7.1 times 10 to the minus 6, which is 7 parts per million, times the magnetic field strength, and it'll be downfield by 0.5 Gauss, if I'm using Gauss as my range. Does that make sense? Now, if this were at 60 megahertz, rather than 300 megahertz, I can multiply, I can take the magnetic field strength used for that kind of an instrument, times 7.1 times 10 to the minus 6, and that turns out to be a downfield shift of, or a magnetic field shift of 0.1 Gauss, and in frequency, it'll be 426 hertz. Now, I'm not going to expect you to do any of these kinds of calculations, but I do expect you to understand the scale we're using. The shift in either frequency or magnetic field strength is in parts per million of that value. Okay? Seems like a real small amount, but we can actually detect it. These instruments are capable of seeing this. Now, some common part per million shifts. These are, again, are shifts downfield from the tetramethylsilane position. Hydrogens on methane, about 0.2. That's not very far downfield. Okay? If I've got methane with a chlorine attached to it, look what the chlorine does. Takes it downfield to about 3. What's up with that? How would you explain that? Yeah, actually de-shielding. Yeah, the chlorine is because it's an electronegativity, tends to pull electrons away from the carbon, which tends to pull electrons away from the hydrogen. It's an inductive effect, and the hydrogens are less shielded downfield by about 3 parts per million. If I put another chlorine on here, the effect is even greater, about 5.3. And 3 chlorines on this thing takes it down in the range we might expect to see with a benzene ring or aromatic hydrogens. Okay? There are lots of tables available to you in your textbook and elsewhere, and you can get online as well and find tables that show these common shifts. Here's an example. And we're not going to read all of these, but just recognize that various things have a range or give us some downfield shifts that are pretty typical. Okay? And we're going to explain, or we'll go through some explanations for some of these things. But you should consult tables like this when you're actually trying to analyze them, because you should see the hydrogens. If you suspect you know what the compound is, it should be consistent with this. Okay, so if you've got ordinary primary hydrogens, it should be around 0.9. But if there's a chlorine next door, you'll expect it to be a little further downfield. In other words, these values give you kind of a starting point, approximate values. But other electron withdrawing groups will have a tendency to cause further shifts. Does that make sense? Like chlorines or bromines and stuff. Now, one of the more pronounced shifts is the aromatic ring shift. And we know that it's down in between about 7 and 7.5. It kind of depends on the structure itself. So here's benzene ring. And I forgot to bring my other slide. Remember that a benzene ring looks like this. And these double bonds can resonate around the ring. So I can think that going to there and that going to there. And now I have new positions for the double bonds that are still conjugated. So this thing will resonate into those two, into that alternate form. It'll look like that. Because this effect is so strong, benzene is often drawn like this, where the circle represents the resonating pi bonds. Okay, that's a common representation. That effect is so pronounced that when I put benzene in a strong magnetic field, those electrons will cycle almost like an electromagnet, and we call it ring current. And they create a very powerful magnetic field. So here's my applied magnetic field. The electrons will cycle in such a way as to create an opposed magnetic field on the hydrogens. Does that make sense? Actually, a sympathetic opposed here. Look what happens. Here's my magnetic field. This guy will experience an added magnetic field because the ring current creates that. Does that make sense? And adding strength to the magnetic field is the same thing as, same effect as the shielding. And so I see the hydrogens on the aromatic ring downfield by about by a ppm of about 7 for that reason. Hopefully you've all seen this stuff before. Same thing with a carbon-carbon double bond. Because these pi electrons are somewhat loosely held, they will actually precess in their pi orbital and create the same effect as the benzene ring. Not as pronounced, not as strong, but we see a downfield shift of these guys between about 5 and 6. So hydrogens attached to a carbon-carbon double bond are going to be quite a ways downfield. And what we're talking, and you need to appreciate this, I think, because at this point, it looks like we're just talking about complexity. Well, this is here and this is here. That's actually good. With proper tables, this tells you what kind of hydrogens you have in your molecule, in your compound. So it's good that there are these kind of differences. Acetylenic, or triple bonded carbons, the molecule itself actually aligns itself in this fashion for this induced effect from the applied magnetic field, and the hydrogens are affected slightly, but not nearly as much. We see these down around 2.5. Not much different than ordinary hydrogens in the middle of the chain. So we see strong effects on an aromatic ring, pretty strong effects on a double bond, and fairly weak effects on a triple bond. Is that all right? Now the aldehyde is very remarkable because there's a carbon-carbon double bond, or carbon-oxygen double bond, and I've got the electronegativity associated with the oxygen. The combined effect of this precessing electrons and the electronegativity of the oxygen takes this thing down to about 9 or 10. Okay, and really aldehydes are about the only thing that's signaled. And it's the hydrogen on the aldehyde carbon that signals in 9 to 10. So you see a peak there, it's very, very likely that that's what you're dealing with. Signals for hydrogens on nitrogen and oxygen are downfield due to electronegativity. These are very approximate. And in fact, there's a pretty wide range where we can expect to see alcohols and amines. Complicating the process, or complicating the situation, these hydrogens, here and here, are acidic enough where they exchange themselves with other molecules. In other words, the hydrogen comes off, remember we're hydrogen bonded, right? And so the hydrogen literally comes off and ends up protonating another alcohol, and then another hydrogen comes back on. And so we have an exchange process going on, which tends to make these signals weak at times, particularly with amines. They'll just look like a little bump on the system. Bond and bump because of the hydrogen bonding, and this exchange complicates this a little bit. So here is a carboxylic